Hey everyone, and welcome! Today we are diving into one of chemistry's coolest puzzles. We're going to find out how a single, simple chemical formula can actually be hiding a bunch of totally different substances. It's going to be fun. Let's jump right in. So, let me ask you something right off the bat. Do you think it's possible for two completely different chemicals, I'm talking different behaviors, different uses, to share the exact same atomic formula? Is that even a thing? Oh, the answer is a huge yes. I mean, just look at this. Take the formula C3H0. If you arrange the atoms one way, you get propanol. That's a liquid antiseptic that boils at almost 100 degrees Celsius. But if you just rearrange those exact same atoms, you get ethyl methyl ether, a gas used as an anesthetic that boils at just 10 degrees. Same parts, but they are worlds apart in what they do.
And this little bit of chemical magic, it's got a name: isomers. This is the solution to our puzzle. See, it's not just about what atoms you've got in the mix, it's all about how they're connected. The structure, the arrangement, that's everything.
Okay, so to really wrap our heads around this, we need to meet the family, so to speak. We need to understand the different ways these molecules can get rearranged. Think of these as the official rules for solving our molecular puzzle. Now, the biggest group, the main family, is what we call structural isomers. This is where the connections between atoms, the very blueprint of the molecule, are just completely different. You know, it's like having a set of Lego bricks. You can use them to build a car, or you can use those exact same bricks to build a house. Same parts, totally different structure. So first up, we've got chain isomerism. Check out butane and isobutane. They're both C4H10. Butane is just a simple straight line of 4 carbons. For isobutane, all we did was pluck one of those carbons off the end and stick it on the side, creating a branch. Same parts, completely different carbon skeleton.
Next, we have position isomerism. This time, the carbon chain itself doesn't change, but a key part of the molecule, chemists call it a functional group, in this case, the little OH group, it just moves to a new spot. You shift it from the end carbon to the middle one, and bam, 1 propanol becomes 2 propanol, which you probably know as rubbing alcohol.
So let's just quickly recap the big types of structural isomers. You've got chain isomerism, where the carbon backbone changes shape. Position isomerism, where a specific group just moves to a new address on that backbone. Functional group isomerism, that's like our very first example where C3H8O could be an alcohol or an ether. And then there's metamerism, which is all about how carbon chains are arranged around a central atom, like an oxygen.
Now, I know this can seem like a lot to keep track of, but here's the cool part. Chemists have figured out some awesome shortcuts. We can think of them as cheat codes that let us predict what kinds of isomers are even possible just by looking at the formula. Check out this table. It's all about looking for patterns in the ratio of atoms. For instance, if you see a formula like CnH2n, that tells you it's missing 2 hydrogens compared to a standard chain. And that missing pair is a huge clue. It tells you there has to be either a double bond or a ring structure somewhere. Or look at CnH2n plus 2O. Hey, that's the pattern from our first example, and it's a dead giveaway that you should be looking for both alcohols and ethers. But here's the thing, and this is really important. The goal isn't just to memorize these patterns. It's about building an intuition. I love this quote from a chemistry teacher who said, "You need to feel the formulas." If you can understand why a certain ratio of atoms forces a double bond or a ring, well, that's way more powerful than just memorizing a rule. All right, enough theory. Let's get our hands dirty and actually put this into practice. Right now, we are all going to become chemical detectives and solve a molecular puzzle together. Let's crack the case of C4H10O. So here is our challenge. Using everything we've just talked about, the rules, the cheat codes, how many different unique molecules can we possibly build with 4 carbons, 10 hydrogens, and 1 oxygen? Go on, take a quick guess before we dive in. Okay, so where do we even begin? Well, like any good detective, we start with the clue, the formula itself, C4H10O. Then we pull out our cheat sheet. That formula perfectly fits the CnH2n plus 2O pattern, where our N is 4. And just like that, we know exactly what we're hunting for. 2 families of molecules, the alcohols and the ethers. Let's find all the alcohols first. We can start simple with a straight 4-carbon chain. From there, we can get 2 different position isomers, just by moving that OH group from the first carbon to the second one. Okay, what's next? Well, let's try a branch chain, a 3-carbon chain with 1 branching off. And that gives us 2 more spots to put our OH group. So just like that, we found 4 different alcohols. Now for the ethers.
Remember, an ether is basically an oxygen atom with carbon groups on either side, like a little sandwich. So with our 4 carbons, we could split them evenly. 2 carbons on one side, 2 on the other. Or we could split them unevenly, 1 on one side and 3 on the other. And wait, that 3-carbon chain could either be straight or branched. So that gives us 3 totally distinct ether isomers.
So, you ready? We found 4 unique alcohol isomers. We found 3 unique ether isomers. You add them up, and what do you get? 7. A grand total of 7 completely different molecules, all hiding inside that one little formula, C4H10O.
Now, this might just seem like a really clever puzzle, and it is, but understanding isomers is so much more than that. It has huge, real-world consequences in things like medicine, new materials, you name it. This isn't just an academic exercise, it's absolutely fundamental.
And if you take one thing away from this, let it be this. The whole reason we care so much about isomers is that different structures mean different properties. A tiny change in how atoms are arranged can be the difference between a life-saving drug and something completely useless, or even dangerous.
Let's just go back to our C4H10O puzzle one last time, because it shows this perfectly. The alcohols we found can form these special connections between them called hydrogen bonds. Think of them like tiny little magnets pulling the molecules together. That's why they have higher boiling points and are great as solvents. The ethers, on the other hand, can't do that. So the molecules fly apart really easily, making them volatile gases, which is perfect if you need an anesthetic. Same formula, totally different jobs, all because of the structure. So I guess that leaves us with one final thought to chew on. If a single, seemingly simple formula like C4H10O can hide so much complexity, 7 different realities tucked inside of it, it just makes you wonder, what other incredible molecular puzzles are just waiting out there to be discovered in the world all around us? Thanks for watching.